Hello everyone, this is Lecture 12 of ComSci 141, Equivalence of PDA and CFG. In the previous video, we discussed the pushdown automata and how to write its 7-tuple notation, how to write its instantaneous descriptions, the difference between PDA by final state and empty stack, the difference between non-deterministic versus deterministic PDA, and how to design pushdown automata. We are now on our fourth topic for context-free languages and pushdown automata, which is the equivalence of PDA and CFGs. So in today's video, we will be discussing how to convert from PDA by final state to PDA by empty stack and PDA by empty stack to PDA by final state. We will also discuss the equivalence of PDA and CFG by showing how to convert from a CFG to its equivalent PDA and converting a PDA to its equivalent CFG. Okay, so let's start. So far, we have seen two notations for our context-free languages, and that is context-free grammars, which is the structural representation, and the pushdown automata, which is the automata version for context-free languages. We have seen that context-free grammars have four parts, and that is the variables, terminals, productions, and the start symbol. Whereas for pushdown automata, it's made up of 7 parts. We have Q, which is the set of states, sigma, which is the set of input symbols, delta, which is the transition function, Q sub 0, which is the start state, F, which is the set of final states, gamma, which is the set of stack symbols, and Z sub 0, which is the start symbol on the stack. We have also shown in the previous video that the PDA can be defined by in two ways. Okay, so you can define a PDA by final state or by empty stack. So a PDA by final state would be defined as follows. So the language of the PDA is defined by the set of strings W such that, so if you start at this instantaneous description, so if you start at the start state Q sub 0 and you start with the input string W and Z sub 0 on top of the stack, then eventually it will go to, so that's the goes to star some ID F epsilon S, and this means that from Q sub 0, which is the start state, eventually we go to F, which is a final state, and we have finished processing the string. So from W it became epsilon or empty, and regardless of the stack contents S. Okay, what's important is we reached a final state after processing the input string. So that is PDA by final state. Okay, on the other hand, PDA by empty stack is defined as follows. So N of P, or the null stack language, is the set of strings W such that, again, if you start with the same instantaneous description or ID, so you start at the start state Q sub 0 and then you start with the string W and the start symbol for the stack Z sub 0, eventually, so it goes to star in 0 or more steps. Some state Q, we don't know or care what that state is, as long as we finished processing the input string. So from W it became epsilon and the stack contents became empty, so it became epsilon as well. So in this case, literally empty. Okay, so that is PDA by empty stack. So take note that the term empty stack has two different meanings in these two different types of describing the PDA language. In PDA by final state, an empty stack means that it only has the Z sub 0 or the bottom marker in the stack, because that means that there is no other any other stack symbol inside the stack, because it's only the bottom marker, right? Whereas in PDA by empty stack, it literally means empty, so there are no contents in the stack, so it's literally epsilon. Okay, so empty string siya. Okay, so that's the slight distinction between the two. We also mentioned in the previous video that a PDA by final state has an equivalent PDA by empty stack, and the same is true for PDA by empty stack. It also has an equivalent PDA by final state, and it's really quite easy to convert between the two. So if I give you an example, we've seen this PDA already from the previous video. So it's the PDA for 0n 1n. So remember that the idea for this was to push zeros on top of the stack. Push a marker X on top of the stack when you see a 0, and when you see a 1, then you pop off that marker, right? But this is basically a PDA by final state, because eventually, after we finished everything and we see the bottom marker, then we transition to the final state F, right? So this is PDA by final state. And to convert this to PDA by empty stack, it's really quite easy. You only need to change this last entry here in the transition function, and it would be like this. Okay, so again, from this one, it becomes this one. So the only thing that that changed was, instead of transitioning to a final state F, we stayed at state P, okay, but instead of having the bottom marker Z, we replaced it with epsilon to make it literally empty. And that's the only thing that you need to change. Okay, and then if you have the opposite, if this was empty stack, okay, so this one naman is for AN B2N, wherein you push 2x's every time you see an A, and then you pop off 1x every time you see a B, because they're supposed to be 2 times the number of B's as the number of A's, right? But this one is a PDA by empty stack, because upon reaching the bottom of the stack, okay, bottom marker, then you will transition to an empty stack by actually removing the bottom marker. Okay, so if this is your PDA by empty stack, to make it a PDA by final state, then we'll also just change this last entry in the transition function and make this FZ. So instead of P epsilon, we won't stay at state P, but instead we'll transition to state F, and we will keep the bottom marker as is. So it's really quite easy. Okay, so that's it for the conversion from PDA to empty stack and final state, and vice versa. Okay, so let us now focus on the main part of this lecture, which is the equivalence of CFG and PDA. So since the two representations represent the same language or set of languages, which is the context-free languages, then it's easy to see that they are also equivalent in language defining power, such that if you are given a CFG, let's call it G, we can create a PDA, let's call it M, such that the language of M is the same as the language of G, or in other words, they are equivalent. Okay, or if you do it the opposite way, given a PDA M, we can create a CFG G such that the language of the grammar G is the same as the language of the PDA M. Okay, so that is the definition for the equivalence of the CFG and PDA. So let's start with the first part, which is converting a given CFG to an equivalent PDA. Okay, so this is the first part of the equivalence. So if we are given a context-free grammar G, so we know that grammar G has 4 parts: the variables, terminals, productions, and the start symbol. We will create an equivalent pushdown automata M with the 7 parts, okay, of the 7 tuple notation, such that they accept the same language. So the language of M is the same as the language of the grammar G. Okay, so how do we convert a CFG to PDA? So here's how. So for the states of the PDA, we will have 3 basic states. We have Q sub 0, Q sub 1, and Q sub F. So Q sub 0 would be your start state. Okay, Q sub 1, this is your, we will call this the work state. This is where all the work gets done actually. Okay, and then Q sub F is your final state. Okay, so this, you only transition here if the string is supposed to be accepted already. Okay, and of course the only final state would be Q sub F. Then Q sub 0 would be the start state also. Okay, So those are the states. We only need 3 states. Next, for the input symbols, that would just be the terminals of your grammar. So for sigma, the input symbols of the PDA, it will just be directly equal to T, or the set of terminals for the grammar. Now for the stack symbols, we can add the variables and terminals of the grammar onto the stack. So we can push the variables, we can push terminals onto the stack. So our gamma, or the set of stack symbols, will actually be the set of variables of the grammar union the set of terminals union the bottom marker z sub 0. So whatever marker you'll choose, it's also included in the set of stack symbols. Okay, but the key thing here is that you're allowed to push variables and terminals onto the stack. Okay, so and then of course z sub 0 is just the bottom marker, the start symbol of the stack. And then finally, for the transition function, this is the most important part of the PDA, right? So how do you create the transition function? So there's actually 4 types of entries in the transition function. So this is the first one. So the first one is, given that you're in the start state q sub 0, without reading any input, so it's epsilon, and we can do this because we already said that the PDA is like an epsilon NFA with a stack, right? So we can transition on epsilon, so we can have epsilon transitions. So again, we are in the start state and without reading anything, so it's epsilon, and we see the top of the stack, which is the bottom marker. We will just transition to Q1, which is the work state, and push the start symbol of the grammar on top of the stack. Okay, so S here is the start symbol of the grammar. Okay, so start state Q sub 0, on top of the stack is the bottom marker Z sub 0. We don't read any input symbol yet, so that's why it's epsilon here, and we will just transition. We know that the derivation of the strings in the CFG starts with the start symbol, right? So of course we will push the start symbol on top of the stack. So push it, push the start symbol onto the stack and transition to the work state Q1, because as we said, Q sub 1 is where all of the work gets done, right? Okay, so that's the first part of the transition function. Next, okay, so we know that the grammar has several productions. So for each of these productions, for as long as they are not epsilon productions, so for each non-epsilon production, A to beta, so A here is a variable, and then beta could be a combination of variables and terminals, right? So because the right hand side could be mixed, okay, so it could be pure variables, pure terminals, or a combination of both. So for each production A to beta in the CFG, we will add the following transition function entry. So from Q1, it's the work state, we'll stay at Q1, and without reading anything, if A, the variable A, is on top of the stack, then we can replace it with the right hand side, which is the beta, which is a combination of variables and terminals. Okay, so because we do this because in the derivation we can replace the variable A with the right hand side of one of its productions, right? So we can substitute A with one of its productions. So we will also do that in our PDA. Once we see a variable A on top of the stack, we can replace it with one of its right hand side productions. Okay, so yeah, we will do that for each non-epsilon production. A is to beta. Now, why is it important that this is not an epsilon production? Because if this is an epsilon production, it would be like this, right? A would be equal to epsilon. If this is A equal to epsilon, then this would be A epsilon. And what does A with epsilon here mean? This actually means that we will remove A from the stack, right? We replace it with epsilon. So that's why we cannot do this, because if we do this, then we are basically popping off the variable a, which we don't want. We just want to replace it with one of its right hand side variables. Okay, so we have to make sure that the productions that we're using are non-epsilon productions. Okay, so again, in detail, you stay in Q1, the work state. You don't read any input symbol. You just replace the variable a on top of the stack with beta, which is a combination of variables and terminals. Okay, so that's the second part. Now the third type of transition function entry would be this one. So for each terminal a, okay, so for each terminal of the grammar, then Q sub 1 reading a with a, the terminal a on top of the stack, we will actually pop off that a on top of the stack. Okay, so we will add this form for each terminal a. So what does this mean? We will stay in the work state Q sub 1, so still Q sub 1 here, right? And then pop off the terminal from the stack. So the terminal here on top of the stack is a, right? So we'll pop that off, we'll replace it with epsilon if it matches the current input symbol. So if the input symbol that we're reading and the top of the stack is a match, then we'll remove the symbol on top of the stack, because basically they've already matched and we can move on to the other parts of the string. Okay, so we'll do this for each terminal a. And the last part is this one. So at Q sub 1, the work state, we will only transition to the final state Q sub f if we see the bottom of the marker, bottom marker of the stack z sub 0, and without reading any input symbol. So that means that we've already reached the end of the string and the stack is also empty. So if that's the case, then we can transition to the final state. Okay, so this is already the end, right? There are no more input symbols to process. That's why the second part of the transition function entry is epsilon. So the stack top is z sub 0, so that means that it's only the bottom marker that's left on the stack. So that means that it's basically an empty stack, right? So there are no more variables and terminals that were pushed. They were all removed already. And if that's the case, then we have finished processing everything, so we can transition to the final state Q sub f. Okay, so that's it for the 4 types of transition function entries. So putting all of it together, so again, the first one is from Q sub 0, you transition to the work state Q sub 1 without reading anything. You just push the start symbol of the grammar. So from z sub 0, it becomes s z sub 0. So you push it on top. Okay, and then for each production a to beta, as long as this is not an epsilon production, then we will stay in Q1, okay, and without reading anything, we'll replace a on top of the stack with beta. Okay, and then for each terminal a, if the input symbol is matched by the top of the stack, then we will remove that top of the stack symbol. So a here is replaced with epsilon. Okay, only if they match. And finally, we will transition to the final state if there are no more input symbols to process and we've seen the bottom marker, which means that it's basically an empty stack. So that's when we transition to the final state. Okay, so those are the 4 things that you need to consider for the transition function. So why are we doing this? So basically, you're using the PDA stack to simulate the derivation of a string in the CFG, because we are actually pushing the variables and terminals onto the stack, right? So going back here, so we are pushing the variables like this one, right? This is the start variable or the start symbol. We're pushing it onto the stack, and then by replacing the variable with a series of variables and terminals, we are pushing more variables and terminals onto the stack. and then we are also removing them by popping it off each time we match with the input symbol. Okay, so we push variables and terminals to the stack. The start variable is pushed at the start, and then we only accept if the PDA accepts the string if after completely processing the stack is empty. That means that the pushed variables were replaced eventually by the terminals, and the pushed terminals were popped by matching them with the current input symbol. So they have been accepted by the PDA. Okay, so if all the terminals were popped, that means that it's an empty stack, so we have matched the input string, so that means that it's accepted. Okay, so I hope that you can imagine why we are doing the pushing of variables and popping of terminals. Okay, now take note that the CFG could have more than one production for a variable, like this. So S could be replaced by epsilon, or OS1, or 1SO. Now that means that for the second type, because it says for each production, there will be multiple entries just for this production, right? So this is not a problem because our PDA is non-deterministic anyway. So it can correctly choose which production to use in replacing the stack tops variable so that it will eventually lead to a correct derivation. So remember that if it's non-deterministic, then it has the power to guess correctly. Okay, so it should not be a problem. So let's see an example of how to actually convert a given CFG to an equivalent PDA. So our given CFG here is okay, so let me write down the CFG here. So that's X is equal to A or B or AXA or BXB. So this is actually the set of palindromes with only A's and B's. Okay, so yeah. So how do we create the equivalent PDA? So let's start with the simple ones. So the terminals, set of terminals sigma would just be the the input symbols would just be the set of terminals. So we'll have A and B here, right? So we have two terminals, A and B. So those would be the input symbols for our PDA. Now for the set of states, we will have three states. We'll call that S, T, and F. So S would be our start state, F would be our final state, and T would be the work state. Okay. And then for the stack symbols, gamma, remember that this is a combination of variables, terminals, and the bottom marker. So for the variables, that would just be X. We only have one variable. And then for the terminals, that would be A and B. So we have X, the variable, the terminals A, B, and then for our bottom marker, we will use Z. Okay, so Z is our bottom marker. So finally, we can do the transition function. So remember that the first thing that we'll need to do is transition from the start state to the work state and push the start symbol of the grammars. And since there's only one variable, this is also the start symbol, so we'll push X on top of the bottom marker Z. Okay, so that's why it becomes XZ. And now we are in the work state T. Next, what we'll do is for each production, right, we will replace the variable with the right hand side. So at state T, will remain at state T, so it's still at state T, and without reading anything, the variable X could be replaced by either A, X could be replaced by B, AXA, or BXB. So this is what we mean by replacing the variable with one of its right hand side. So it could be any one of these four. Okay, and then for each terminal, we add the following. So staying at T, okay, if A is matched with a stack top symbol, which is also A, then we will pop off that A. And then we'll do the same for the other terminal, which is B. Okay, so if B is the input symbol and B is also the top of the stack, then we will remove this B on top of the stack. Okay, so we'll pop it off. And then finally, we'll transition to the final state if there are no more input symbols to process and we've seen the bottom marker Z. So we'll transition to state F, which is the final state. Okay, so these are the the five, or actually it's not, it's more than five because this one is multiple, so there's actually 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 entries in our transition function because this counts separate. So this is 1, 2, 3, 4. So there are 4 entries for T epsilon X. So 4 plus this one, this one, this one, this one. So total of 8 entries. Okay. So that's our transition function. And okay, so let's see how this string would have been derived. A, B, 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 A. If we were using the CFG. So in the CFG, we start with X, and then X could be replaced with AXA, then the X could be replaced with BXB, so that we could do this B here, and then the X here would be replaced with B, and then that's it. So A, B, 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 A is derived, so it's accepted as part of this language, right? Now, how about for our equivalent PDA? So we have our equivalent PDA here. So where do we start? We start at state S. A, B, 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 A is the string to process, and then Z is the only thing on top of the stack. So since it's the bottom marker. So after this, we will the first thing that we'll need to do is this one, right? The first the first type of the transition function. So we'll transition to state T and push the start symbol. Okay, so this will go to T, state T, and we pushed X on top of the stack because X was the variable name, right? Or the variable for the start symbol. Then after that, X could be replaced with, what do you think? X could be replaced with AXA here without reading anything. We want AXA because we know that A is the starting symbol. So we could do this. X is replaced with AXA, and we have that here. This X here is replaced with AXA here. Okay, and then after that, since A here is matched with A here, we can pop that off, so it becomes BBBA XAZ. And where did we get that from? This line here. A and A are matched, so we pop off A on top of the stack. And then after that, this X can be turned into BXB so that we can process this one. So X will be replaced with BXB, okay, and that is here. So X replaced by BXB here. Okay, and then after that, these two B's are the same. Okay, so we can pop off the B, so we will be left with BBA XBAZ, right? So this is the remaining ID. And then after that, X can be replaced with another B, right? Because that's possible here, X to B. And then we can pop off B here since that's the same. We can pop off the B here since it's the same. And then we can pop off A since it's the same. And then we are eventually left with T epsilon Z. So since it's already empty, the string has been completely processed and the stack is also empty since only the bottom marker remains, then we can transition to state F because we are in T epsilon Z. So we can transition to state F, and we have reached the final state. So since it reached the final state eventually, then the string is also accepted by the PDA. Okay, so that's just an example of how to convert a given CFG to an equivalent PDA. So that's it for the first part of the equivalence, and we are now ready to move to the second part, which is converting a PDA to an equivalent CFG. Okay, so the second part of the equivalence is converting a PDA to an equivalent CFG. So if you're given the pushdown automata M with its 7 parts, create the equivalent context-free grammar G such that the language of the grammar G is equal to the language of pushdown automata M. So they accept the same language. Okay. However, we're going to make an assumption about the given PDA, and that this PDA accepts by empty stack. Okay. If the given PDA accepts by final state, then we're supposed to convert it first into a PDA by empty stack. Okay. So for the rest of the steps, we are already assuming that it's a PDA by empty stack. Okay. So we will use this PDA as our running example, and it's the PDA for the language 0i 1j, wherein I is greater than or equal to j and both are greater than or equal to 1. Okay, so what this means is it's a series of zeros followed by a series of ones, wherein the number of zeros could be greater than or equal to the number of ones. Okay, because I here is greater than or equal to j, and there should be at least one 0 and at least one j. Okay, or at least 1 0 and at least 1 1. Okay, so it can't be just 0 or just 1. It should be more than or equal to 1. Okay, so what this PDA does is basically more or less the same as the one that we saw with 0n 1n, but this time so if you see a 0, you still push an X as a marker on top of the stack. So each time you see a 0, you push an X on top of it, and then when you see a 1, you transition to state Q1. So you're now processing ones, and the X on top of the stack will be popped off. So the same here, X will be popped off. So if the number of zeros and ones are equal, then we can pop off each X that was pushed by 0, and then all of those zeros will be popped off by the ones. Okay. However, since we are allowed to have more zeros than ones, then there could be more X markers even if there are no more 1 input. So we're also allowed to do this on state Q1 without reading the input, so it's epsilon. The X on top would be popped off. Okay, and why will we do this? Again, because there could be more zeros than ones, because I here is greater than or equal to j. So there could be more markers, X markers on the stack that are available. So we can also pop them off without reading from the input. Okay, and then after that, once we see the bottom marker Z, then we will pop off that bottom marker Z, and this will be accepted because this will now be a literally empty stack. Okay, so yeah, that's the running example. So how do we convert from PDA to CFG? So take note that our CFG has 4 parts, right? Variables, terminals, productions, and the start symbol. So for the terminals, it will just be the input symbols of the PDA, so sigma. Okay, so whatever the input symbols were for the PDA, that would also be the terminals for your grammar. Okay, now the start symbol S would be a new variable, and this start symbol, which is a variable also, represents the set of strings accepted by the language, by the CFG and by the PDA. Okay, so it's a set of strings accepted by the language. Now for the set of variables, it would be S, which is the start symbol, and other variables would be of the form P, X, Q in square brackets. Okay, so let us discuss this form of the variable, because all variables in the equivalent CFG will have this form. Okay, so what does this form mean? So the variable pxq, the p and q here are states, okay, and x here is a stack symbol. Now, what does PXQ mean? So, the variable PXQ represents strings W such that if we start at P and we have the string W and X, this X is currently the top of the stack, okay, eventually, okay, it will go to, so that's goes to star, the state Q, wherein W is now equal to epsilon, so that means that we have processed the whole string, and X becomes epsilon, so that means that we have popped off X. Okay, we have removed X from the stack. Okay, so again, after processing W, so it eventually becomes epsilon. Okay, so it's the yellow epsilon here. The PDA transitions from state P to state Q, and the stack top symbol X and all of its replacement symbols are eventually popped off or replaced with the epsilon. So that is what we mean by PXQ. So from P, the string will be processed. Eventually, it will, from P, currently the stack top symbol is X. Eventually, this will be processed and will reach the state Q such that X and all of its replacement symbols are eventually popped off or removed. Okay? So that's the meaning of the variable PXQ. So if it's only X as the stack top symbol, then it means that we eventually need to pop off X. But if we replace X with ABC, for example, now X has already been replaced, but eventually we need to pop off A, B, and C as well, because the replacement symbols will now inherit the property of having to be removed. Okay, because if we go back here, X and all its replacement symbols have to be popped off. So if we replace X with ABC, although we popped off X because, well, we replace it with ABC, X is essentially ABC now. So these three have to be popped off as well. Okay, so the stack top and its replacement symbols have to be removed. Okay, so now we're ready to create the productions for our equivalent CFG. So there are three types of productions for the equivalent CFG. So let's start with type 1. So what we'll do is, for all the states in the given PDA, for all states P, what we'll do is we will add this production. So S, remember, is our start symbol. S will go to the variable Q sub 0, this is your start state. Z sub 0, this is the stack top, the bottom marker, right? And then P, which is the state. Okay, so we'll have to do this for all states. We'll have to add this production. So the reason for this is because in the CFG, the start symbol derives all the strings in the language. So it has to be, it has to start with S, right? So S must derive all the strings that were accepted by the given PDA if we are to create a equivalent CFG. Now, remember that our PDA, our given PDA, accepts by empty stack, and from the definition of PDA by empty stack, it accepts all strings W such that starting from the start state, starting with this string and with the bottom marker, it eventually goes to an empty stack. So it eventually will lead to an empty stack after processing the whole string. So from W it becomes epsilon, and from the bottom marker it becomes epsilon as well. So literally empty. Okay? So for our type 1 production, the reason why we are adding this production, S equals Q0 Z0 P, is because, okay, so this is what this means. So the PDA starts from Q sub 0 because that's the start state, right? And eventually it ends up in some state P. Okay, so going back here, PDA by empty stack. So we said that from starting from the start state, it will lead to an empty stack, and we end up in state Q. We don't care what this state Q is, right? So we don't know or care what this state Q is as long as it's an empty stack. So going back here, the PDA starts from state Q sub 0 and eventually ends up in some state P. And the reason why we'll add this for all state P is because we don't know or care which state the PDA ends up in. So it could be at state A, state B, or state C. Doesn't really matter as long as there's an empty stack. Okay? So that's why we add this for all states P. Okay? Now, how about Z sub 0? So remember that after processing the string, Z sub 0 and its replacement symbols are popped off the stack. Now, what happens if Z sub 0, which is the bottom marker, is popped off the stack? That means that it's already a literally empty stack, right? So if it's a literally empty stack, then the string is accepted. So that's why for our start symbol S, we are allowed to replace it with this variable, because this variable represents all the strings that are accepted by the PDA. Okay? So again, that is starting from start state, you eventually end up in some state P. You don't know or care what that state is. So that's why you add it for all states P. And by doing so, you are popping off Z sub 0 and all of its replacement symbols. Okay? So if Z sub 0 is popped off, then that means that it's literally empty. Okay? So the literally empty means that it's the language of the PDA. So that will be equivalent to the language of the CFG. Okay? So S yields all accepted strings. Okay, so if we go back to our running example, okay, here, how many states do we have? We only have two states, right? Q sub 0 and Q sub 1. So if we add this type 1 production for all states, Q sub 0 and Q sub 1, we will have two productions that we will add. So S can go from Q sub 0 Z Q0 or Q0 Z Q1. Again, because we have the two states here, Q0 and Q1. Okay, so that's the type 1 production. Now, our ultimate goal in this PDA is to empty the stack, right? To remove all the contents. So all the stack symbols that we push on top eventually needs to be removed so that we eventually have an empty stack. Okay, so the variables of the form PXQ represent eventually popping off X from the stack. So this will be helpful. So that's why this is a helpful form, because this variable represents popping off the stack symbol X from the stack, and that's what we want, right? We want to remove stack symbols so that we eventually can have the empty stack that we want for the PDA to accept it. Okay, so let's now go to the second type of production that we'll add for our equivalent CFG. So this time we'll look at the PDA transitions and find the pop pattern. So the pop pattern basically is looks like this. So starting from state P, it could transition to state Q, or it could be the same. It doesn't really matter, but for some state Q, upon reading A, X on top of the stack is popped off. So X is replaced with epsilon. So this is the pop pattern because we are popping off the top of the stack. Okay, so in here we actually have 4, right? We have this one, this one, this one, and this one. So the last 4 has the pop pattern. So what we'll do is, for each of these transitions with the pop pattern, we will add the production PXQ as the variable is equal to A. Okay, so where did we get this? So P is here, X is here, Q is here, so that forms the PXQ variable, and then on the right hand side we have the terminal A. Okay, or the terminal which made this transition possible. But A could be an input symbol or epsilon. It could be epsilon because take note that we could have epsilon transitions, right? So this one here could be epsilon. So what does this mean? Okay, so upon reading A, right, in our PDA, the PDA goes from state P to state Q, and it pops off X from the stack because X is replaced with epsilon, right? Now that sounds familiar because that is actually the description of this variable, right? It goes from state P to Q, right? So from P it eventually ends up in Q, and it pops off X and its replacement from the stack. So it's exactly this one, right? So that's why this variable can be replaced with A because this happens upon reading A. Okay? So PDA goes from state P to Q, pops off X and its replacement from the stack. So this is done after reading A. That's why we allow the substitution of this variable with A. Okay? So that's why we add this production. Okay? So that's what you do for the pop pattern. Sorry. So if this is the pop pattern, add PXQ as the variable is equal to this one, this symbol or epsilon. Okay? So that is the type 2 production. In the example that we had, I mentioned already that these are the 4 pop patterns here. Okay? So let's see. So if this is the case, so we have 4 of the pop patterns because X is replaced by epsilon, X is replaced by epsilon, X replaced by epsilon, Z replaced by epsilon. That's why these are pop patterns. So what will we add here? So this would be Q0 X Q1 becomes 1. Okay? How about this one, the second one? That would be Q1 X Q1 becomes 1. Okay? And then, okay, so let me remove the other marking so that it's not. Okay. For the third one, that would be Q1 X Q1 equals epsilon. And then finally, Q1 Z Q1 equals epsilon as well. So those are the 4 productions that we add for the 4 pop pattern transition function entries. Okay? Now, for the type 3 productions, which is the last type, instead of the pop pattern, we will find PDA transitions with the replace pattern naman. Okay, so the replace pattern is basically this. So from state P, you transition to some state Q. On input symbol A, the stack top symbol is X, and you replace that with beta, wherein beta is one or more stack symbols. Okay, so it's a replacement basically. So some examples of replacement would be from X it becomes still X, so you actually don't do anything. From X it becomes Y, so you replace it. X it becomes YZ, so you removed X and added Y and Z on top, or even more, the WYZ. So these are all examples of replacements, and assuming of course that W, X, Y, and Z are stack symbols. Okay, so what will we do with these replacement examples? So going back to our example, we have of course 2 that follows the replacement pattern, because here Z is replaced with XZ and then X is replaced with XX. Okay, so those are the 2 transition function entries that follow the replace pattern. Okay, so what will we do when we encounter the replace pattern? Okay, so Okay, so for the first case, what if it's not really a replacement, right? It's still the same. X becomes X. So to remove X and its replacements, so you did not really replace it because it still remained as X. Starting from state P, okay, so our goal is to eventually pop this off, right? So you're starting at state P, and your goal is to remove X eventually, right? So reading A causes the transition from P to Q, right? So if you read A, you transition from P going to state Q, okay? But you only transition from P to Q, you did not pop off X, right? Because X is still there, right? So this is Q. In state Q, X is not yet removed. So you'd have to imagine that from Q, it went to some other state wherein X got popped off, okay? And we can actually have a variable for that, and that is the state or the variable Q X R. Okay, so what does Q X R mean? So you're in state Q, and since your goal was to remove X, then you remove X and its replacements from the stack and end up in some state R. So from Q, you transition to R. Okay, so eventually you ended up from starting from P, you ended up in state R, and you have removed X. So you ended up in state R after everything. So that would be P X R. So starting from P, you ended up in R, wherein you replaced X, and the way to do that is by doing this. Okay, so let me replace that with a cleaner version. QXR. Okay, so again, why is that? Because A as the input symbol allowed you to transition from P to Q, and then this variable QXR represents starting from state Q, eventually leading to R and popping off X. Okay, so yeah, so that's it. PXR is equal to AQXR. So from state P, you remove X and its replacements and end up in some state R. Okay, and the way to do that is starting from A, you transition from P to Q, and then from Q, since X has not been removed yet, then you create this variable QXR that represents starting from Q, removing X and its replacements, and ending up in some state R. Okay, so that's why you also end up in state R here. Okay, now what if it was actually a replacement? Like from X, it became Y. Okay, so to remove X and its replacement Y, starting from state P, so that would be you start at state P and your goal is to remove this X, right? Okay, so we don't know what state we'll end up in yet, but for now, we know that if we read input symbol A, this causes a transition from state P to Q, right? Because from P, if you read A, it becomes Q. Okay, and the X here is replaced with Y. Okay, so you have already removed X. Okay, that's okay, but now your goal is to remove Y. So you're now currently in state Q. Okay, so your new goal is to remove Y and its replacements starting from state Q, and your goal is to remove Y. So this is represented by the variable Q Y R. Why is that? Because QYR means that you're in state Q, you eventually end up in some state R, Okay, but um, the effect is you removed y and all of its replacements from the stack. Okay, so in the end, we ended up in state R because we have removed x and all of its replacements, because this variable here represents that. So we have pxr is equal to aqyr. Okay, so if we remove everything to make it cleaner, pxr is equal to aqyr. So again, pxr means that you start from state P, you remove x and all of its replacements, and ended up in some state R. And you do that by starting from A. So the A here makes you transition from P to Q, right? And then from Q, transition from Q to R. And from P to Q, it allows you to replace X with Y as the stack top. And then from Y is popped off by this variable. Okay, so X and all of its replacements have been removed from the stack. Okay, that is if it's a simple X to Y. How about if it's X to Y and Z? What will happen now? So to remove X and its replacements, Y and Z, starting from state P, so what will we do? We will have to start at P, right? So from P, our goal is to remove X and all of its replacements, and we do that by starting with input symbol A. So from input symbol A, we have the stack top X, right? But from P, we're allowed to transition to Q. Okay, so from P to Q, we can do that on input symbol A, and X becomes Y, Z now. Okay, so X has been removed, so this is okay already. We can cross that out. But now Y and Z has to be removed. But now we are starting at state Q. So at state Q, our first goal is to remove Y. Okay, so maybe we can use the variable qy, and then we end up in some state R1. Okay, but in here we transition from state Q to state R1, and we don't know what that state R1 is for now, but eventually we popped off Y. So now we're left with Z na lang. Okay, so for Z, starting at R1, so that's R1, will pop off Z and end up in some state R2. Okay, so from R1 you ended up in R2, but you popped off Z, so everything is now removed, and this is the form. So eventually it ended up in R2. Okay, so again with the steps, reading A causes the transition from P to Q and replaces X with YZ on stack. So if X is removed but it's replaced with YZ, so our new goal is to remove Y and Z and its replacements. So since our first goal is to remove Y and its replacements from starting state Q, because we transitioned from P to Q on A, so that would be QY R1. Okay, so starting at Q, you remove Y and we end up in some state R1, but we remove the first replacement, which is Y. Okay, and then the second goal is to remove Z, the second replacement, from the current state R1, because we're now in R1, right? So that would be R1 Z R2. So we're currently in state R1, remove Z and its replacement, and end up in some state R2. So that's why we will add this production. So PX, and then this one here is the last state that you end up in. So you start at state P, your goal is to remove X, you end up at some state, whatever last state is here, R2, and you do that by starting at the input symbol that made this transition from P to Q, and then from Q it becomes you have the variable QYR1 to represent starting at state Q, popping off y and its replacement and ending up in some state R1. Then from state R1, you have the variable R1, Z, R2 to represent the strings that you have. If you start at R1, remove the stack symbol Z and end up in some state R2. Okay, so from state P, you remove X and its replacements. So that's it. So the general form of this is something like this one. So if you have P, A, X is equal to Q with this replacement. So P and Q are the states, A is the input symbol, and then X is the stack top symbol, and then these are the replacements, wherein K could be greater than or equal to 1 because we don't know how many replacement symbols there are on this side of the transition function. So if there are K symbols on the replacement, we will also use K variable states. So R1, R2 up to RK. Okay, so remember earlier we used just R, and then on this next example we used R1 and R2. So however many symbols there are in the replacement, that would be the same number of variable states that we'll use. Okay, so the general form would look like this: Px Rk. So the last state would eventually be R sub k, which is the last state, and then you start at A, and then starting at Q, you remove Y1 and end up in R1. Then from R1, you remove Y2 and end up in R2. From R2, you remove Y3 and end up in R3, and so on until you remove the last replacement stack symbol and you end up in state R sub k. Okay, so that's the general case. So we generally don't know what the states R1, R2 up to RK are, so we'll try that for all possible combinations because we don't know or care what the states are that they end up in. As long as you pop off the stack symbol that we are interested in, we don't really care which state we end up in, right? So yeah, we'll try this for all possible combinations. So for this example, if we have this one, how would this look like? So this would be, of course, P here, and then X is the symbol that we're supposed to remove, and then how many variables should we use? Since there are 3 replacement symbols, then we would use R1, R2, and R3. So we know that we'll eventually reach R3, right? So how will we do that? We start with A, and this will allow the transition from P to Q. So we're now at state Q. At state Q, we can remove W, which is the first replacement symbol, and end up in variable state R1. From R1, we can remove Y here and end up in state R2. And from R2, we can remove this stack symbol Z here and end up in R3. So we have now removed all of the replacements of X here, W, Y, and Z, because they have been removed by these variables. So this is the production for this transition function entry. So again, 3 variable states, and it's Px R3 is equal to A Q W R1 R1 Y R2 R2 Z R3. Okay, so yeah, it seems complicated at first, but once you get the pattern, it's really quite straightforward. Okay, so just be patient with it. Okay, so for our example, we said that these 2 here are following the replace pattern. So how would that look like? For the first one, Q0Z becomes Q0XZ. So what would happen? This would become how many variable states would there be? There would be 2 because we have 2 replacement symbols. So this would be Q0, and then Z is what we want to remove, and then eventually this will end up in R2, right? So R2. And this becomes starting at 0. So 0 allows you to transition from Q0 to Q0. But since you're still at Q0, we'll start at Q0 and then remove X here, X, R1. So we're now at R1. So we'll start at R1 and then we remove Z and then R2. Okay, that's why we end up in R2 here as well. So again, variable states are R1 and R2, and then you have the Q0 ZR2 is equal to 0 Q0 X R1 R1 ZR2. Okay, now R1 and R2 could either be Q0 or Q1, so we'll have to test for all possible configurations. So that would be 2 states times 2 options, so 4 possible combinations. So the combo for R1 R2 could be Q0 Q0 Q1 Q1 Q0 Q1 or Q1 Q0. So you have to test for all possibilities. Okay, so that's the first one. For the second one, it would be this one, right? So we'll still have 2 variable states, R1 and R2. So we'll start with Q0, want to pop off X and all of its replacements. And since we know that there are 2 variable states, we know that this will end up in R2. Okay, so the right hand side will start with this 0, which allows us to transition from, well, it stays at Q0, right? So this will start with Q0, we'll remove X and end up in R1. And from R1, we'll also remove the second X and end up in R2. Okay, so that's Q0 X R2 is equal to 0 Q0 X R1 R1 X R2. And again, R1 and R2 could either be Q0 or Q1, so you have to test for all possible combinations. Okay, so that's the example for type 3 productions. So all in all, we have the 3 types of productions for CFG. First is for each state, we have to add this for the start symbol. So S is equal to Q0 Z0 with the state P, because we don't care what state we end up in, for as long as starting from the start state, we will remove Z0, which is the bottom marker, to make the stack literally empty. And then for each pop pattern in the transition function, we will follow this pattern for the production. So that's P X Q as the variable is equal to A, because that means that we transition from P to Q and popped off X, right, on input symbol A. And finally, the third type of production is following the replace pattern, right? So X is replaced by this string of stack symbols. So you start at P, you want to eventually pop off X and its replacement symbols, so you'll have to eventually end up in some state R sub K, and you do the replacement by starting at A input symbol, which allows you to transition from state P to Q. But from Q, you're now supposed to remove Y1 and end up in some state R1. From R1, remove Y2, end up in some state R2, and so on until you remove the last replacement symbol and end up in some state RK, which is your last state anyway. Okay, and since these are variable states, you will have to test for all possible combinations of the variable states. Okay, so yeah, going back to our example, we had this 2 as our type 1 productions because we have 2 states, right, Q0 and Q1. For type 2 productions, we had the 4 pop pattern, so that's why we had this 4 productions as well earlier. And then for the type 3, there are 4 possible productions of this kind, because we have R1 and R2 being Q0 and Q1 for both. So that's 2 times 2 is 4 possible combinations. So if you actually replace R1 and R2 with the possible Q0 and Q1s, this would be the whole list of productions. So if you put all of that together, okay, wait. Oh, it's here. So if you put all of that together, it would be this one. So these are all of the productions for our example PDA. Okay. So let's now try to see some input strings if they really work with our PDA and our equivalent CFG. So in our PDA, remember that we're supposed to push X once we see a 0, and then once we see a 1, we're supposed to pop it off, and it's allowed to have more X's than more X's in the stack, even if there are no more 1s, because there could be more 0s than 1s, right? So starting at the start state Q0, this is the string, and the bottom marker is Z. So since we see a 0, we'll push X. We see another 0 here, so we'll push another X. We see another 0 here, so we push another X. So the 3 zeros here have been replaced with 3 X's on the top of the stack. Now since we see a 1, we'll pop off this X, so this becomes 2 X's na lang on top, right? And then see another 1, pop off this X, so it becomes empty, and there's still an empty extra X. But as we mentioned earlier, you're allowed to transition to, or you're allowed to pop off the X even without any input, right? Since there could be more zeros than ones. So we could also pop off this X, and it becomes Q1 epsilon Z. And once you're in this state, remember that you're allowed to go to so you're in Q1 EZ or epsilon Z. Okay, so you are now allowed to pop off Z as the bottom stack marker. So that means that it will now become literally empty. Okay, so it will now become Q1 epsilon epsilon. So we have now reached an empty stack, and it is already accepted. Okay, since this is a PDA by empty stack. Okay, so the string 00011 is accepted because there are more zeros than ones. Okay, now how about for our equivalent CFG? How would we do the derivation? So of course we'll start with S, right? Start with S. Okay. Maybe here. Okay, so we'll start with S. So that's our start symbol. And going back here, there are two possible replacements for S. It could be this one or this one. Now, how would we choose which one? Well, the intuition here is that eventually we want to replace the variables with terminals, right? But you'll notice that the terminals are found here. 1, 1, and then epsilon, epsilon. So you'll also notice that all of them ends with Q1. So it might do us good to choose this production because it ends in Q1 instead of Q0. So we'll choose this one. S becomes Q0 Z Q1. Okay, so S Q0 Z Q1. Now we can replace this variable with another one. So since we want a 0, okay, so which variable, which production allows you to replace Q0 Z Q1? So going back here, we have two options, no? So we either have this one Q0 Z Q1 or this one Q0 Z Q1. So these are the two possibilities, right? So it's the only difference here is that it's either Q0 as the intermediate or Q1 as the intermediate. But again, we'll notice that if we want to replace this eventually later, there are no replacements for Q0 x Q0 that is a terminal, right? Because the only replacement for a terminal could be if it was Q0 x Q1, and that would become 1. later on, right? Because Q0 X0 will just form more variables here. And since we want more terminals, then we will choose this one, the fourth production. So we'll replace Q0 Q1 with 0 QOX Q1 Q1Z Q1. So that one is here. So we have the intermediate Q1 and then X and Z. Next, this variable will have to be replaced. Okay, so Q0 X Q1. So going back here, Q0 X Q1, these are the two possibilities here at the bottom, the last two, right? So again, for the same reason, I don't want to use this one, because if I want to replace this with the terminal later on, there are no replacements for terminals, whereas this one, Q0 X Q1, has replacement, which is 1, right? So I will use the last production here, or the last, to replace Q0 X Q1. So that would be 0 Q0 X Q1 Q1 X Q1. So this one will be replaced with this. Okay, so after that, our next variable to be replaced is the same. It's still Q0 X Q1, just like what we had here. So I'll actually use the same production to replace it. So it's still the same. Okay, so I will also replace this one with this one. So that's why we have now 3 zeros, and then we still have Q0 X Q1 here, Q1 X Q1, and then the rest here, Q1 X Q1, Q1 Z Q1, are still there. Okay, so now I have my first 3 zeros. My goal now is to replace it with a 1. So our next variable is Q0 X Q1. And if we look here, Q0 X Q1 can be replaced with a 1, right? Which is convenient. And that is actually the reason why we chose this and this over their counterparts, right? Because we wanted to replace it with a 1 eventually. So Q0 X Q1 will be replaced with a 1. So in the next slide, it now becomes 1, and then the next variable is Q1 X Q1, which is here earlier, right? It was this one. So this variable now, Q1 X Q1, becomes which one? Well, we want it to be 1 also, right? So we'll use this production. Q1 X Q1 becomes 1. So we'll replace that with the 1, and now we have found our string. But we still have some variables here left, right? So Q1 X Q1 can be replaced with an epsilon, right? So we will replace it with epsilon. So it becomes epsilon, and then finally the last variable, Q1Z Q1, can also be replaced with a epsilon through this one, right? The last one. So that also can be replaced with an epsilon, and now we have derived 00011. Okay, so since it was eventually derived, it's also accepted. Okay, so it also accepted the string that was accepted by the PDA. So yeah, this is the equivalent CFG from a given PDA. So that's it. We have discussed the equivalence of PDA and CFG by showing you that we can convert from a CFG to an equivalent PDA and vice versa. So the steps for CFG to PDA are as follows. You create the states by having 3 states, basically the start state, the work state Q1, and the one final state. The stack symbols would just be the union of variables, terminals, and the bottom stack marker. And then from for the transition function, we start with this one. So from the start state, you go to the work state, and then you push the start symbol on top of the stack. And then for each non-epsilon production, A is equal to beta, then you replace A on top of the stack with beta, which is a combination of variables and terminals, without reading any input. Okay, and then for each terminal A, once we see A on the input and A is also on top of the stack, then we will pop off that A on top of the stack so that we can match it with the input symbol. And then finally, once we see a empty stack, so it's only the bottom marker and without any input symbols left, then we can transition to the final state. Okay, so that was the equivalent PDA. Now for the PDA to CFG, we had variables of the form PXQ, which meant that you transition from state P eventually to state Q, while eventually popping off X and its replacement symbols from the stack. Okay, so for the productions, we had three types, starting with this one. So for the start symbol, we transition we can replace that with the variable Q0 Z0P, because this means that starting at the start state, we end up to some state P. We don't know, we don't care what that state is, for as long as we remove Z sub 0, which is the bottom marker, and all of its replacements. So that means that it's a literally empty stack. And since we don't care what the state P is, we will do this for all states P. And then for all the pop pattern transition function entries, we will add this production. So PXQ is equal to A. And then for the replace pattern, we have this general form, right? So PXRK is equal to A, QY1R1, R1Y2R2, and so on until we popped off all of the replacement symbols on top of the stack. Okay, so that's it for equivalence of PDA and CFG. For our next topic, we will be discussing properties of context-free languages. So we'll discuss closure properties, decision algorithms, and the pumping lemma for the context-free languages. And this would be our last topic for context-free languages, or for our second long exam topics. Okay, so that's it for this video. And if you have any questions, don't hesitate to ask, and I will see you in the next video.